In section 1.8, we're going to discuss what's called continuity of a function. Consider the following function in this graph given here. Let's compute these three things. We already know how to compute this, so this is kind of review, but it's going to kind of illustrate the importance of what it is that we're going to study in this section here. If I can write here, there we go. So as we're approaching -2 from the left, the function is heading toward, the y value is heading towards 3. As we're approaching from the right, the y value appears to be approaching, well, it's not quite, we'll just call it 1 or -1. It looks like it might be slightly below that, but maybe I'm just not looking at this straight on. And then what is f of 2? The value of the function is going to be, the y value there is 1 because there's a point there. Notice that all three of these are different. And this is kind of unpleasant. The function is rather unbehaved. It's kind of a mess at x equals 2. So we can avoid this, so what we have here at 2 is we have an example of where the function is not continuous. It's discontinuous. So what does it mean to be continuous? So a function f is called continuous at any x value, x equals c, and here's the important thing. I'm underlining it, and this is in red, inside of the domain. We're only checking this inside of the domain of the function, these properties, if it satisfies all three conditions below. First, f of c exists. Second, the limit as x approaches c of f of c exists. And third, the two match up. We say that f is continuous if it is continuous at every x equals c inside of the domain. Now, I prefer a slightly different definition, which is equivalent to this. I tend to prefer to remember this definition of continuity in the following way here. If we say that a function f is continuous at x equals c, and again, inside of the domain of the function, if the limit from the left is equal to the limit from the right is equal to the value of the function, and provided that all three exist. Because essentially this is what you're checking, whether you're checking things by looking at the graph or whether you're checking things sort of algebraically, just by looking at the formula of the function, if you're checking it kind of that way, or if you're looking at the graph. These are the three things that you're checking, that they match up. This is what it means to be continuous. Okay, so let's look at some examples. Is this function f of x equals 1 over x minus 6 continuous? Let's graph what it looks like. Okay, so we know what this looks like. If we just use some transformations that we learned earlier in the chapter, we know that it's going to be the reciprocal function. We just shift that asymptote over to 6. So this is what it's going to look like right here. Okay, so this is what the graph looks like. And you may say to yourself, wait, this is definitely not continuous. There's an asymptote here. There's a break in the curve. And you're absolutely right, there's a break in the curve. But you're not absolutely right that it's discontinuous. Because here's the important point, and I put this in red. We're only checking inside of the domain. Inside of the domain, we have to check these three properties here. That the limit from the left equals the limit from the right equals the value of the function. 6, x equals 6, is not inside of the domain. What is the domain? The domain is everything but 6. We avoid 6 because it's not defined there. F is continuous on that set. Because everywhere but 6, it's very well defined. If we pick this point here, for example, the value of the function is equal to the limit from the left is equal to the limit from the right. The same can be said for any other point inside of the domain. So f is continuous on its domain. In other words, if it's continuous on its domain, we don't even say it's continuous on its domain. We just say that f is continuous. In other words, is this continuous? The answer is unequivocally yes, it is continuous, since it's continuous on its domain. Okay, so this is where it's a little bit tricky. You have to make sure you're checking this only on its domain. Here's some properties that we can use to make determining continuity a little bit easier. So first, well, what are we assuming? So suppose that f and g are both continuous functions at a point x equals c in their domains. Then so are the following functions at that common point x equals c inside of the domain. So if it's continuous, if f and g are both continuous at x equals c in the domain, then so is the function f plus g, so is f minus g, so is any constant multiple of f, so is f times g, so is f divided by g, provided that g of c is not 0, so is f to the n, or the nth root of f, and I should say it's the nth root of f, provided the nth root of f makes sense. Provided you're not taking the square root of f at c, which would result in a negative number that you're taking a square root of, for example. What can we do with those properties? We can get, here's the consequences that we get out of that. And this is really cool. So any polynomial is continuous. Why is that? Okay, so first off, a constant function, I think all of you, I mean, anyone would agree that just looked at the definition that this constant function is continuous, right? And you'd probably also agree that y equals x is continuous, right? From there, we can use those limit properties to build up to any polynomial being continuous. Because if these two functions are continuous, then so is the function a1 times x, where a1's a constant. This is continuous as well. If this is continuous, then so is the sum of a1x plus a0. That's a continuous function. If that's continuous, then so is the function x squared. Since x was continuous, if you square it, it's also continuous. If you then multiply it by a constant, it's also continuous. If you then add it to the previous continuous function, it's also continuous. And you can just continue going through this process, building up to any polynomial being continuous, only needing to convince yourself and others that these two functions are first continuous. And then using these properties over and over and over. In particular, we're just using 1, 3, and 6. Okay, so we know that any polynomial is continuous. Now that we know any polynomial function is continuous, any rational function has to be continuous as well. Because a rational function is just a polynomial divided by a polynomial. If two functions are continuous, then so is their quotient, or if you divide the two. Except for where q of x could be 0. Any root function is continuous on its domain. A root function is just simply taking a root of a linear function. I think that's typically what we mean by a root function. So this is a continuous function if you take a square root or some kind of a root of that, as long as it makes sense on its domain, then it's continuous as well. Any trig function is continuous on its domain, and I wanted to emphasize that this does not follow from the properties. There's other arguments that are needed to get that. Okay, so we have lots of examples of functions from our basic catalog of functions that are continuous. Polynomials, rational functions, root functions, and trig functions, all continuous. Let's go ahead and pause here. So we'll stop here with this particular video, and we'll pick up with looking at other examples of functions, trying to see if we can determine where they are or are not continuous. So at this point, if you'd like to practice some WebAssign homework problems on your own, I think you can do the first problem. Yeah, I think you can do the first problem and probably stop there.